So the focus for today's lecture is to look now at the wave functions, the bound state wave functions for the finite square well. We had previously found a very beautiful set of solutions for the energy levels of those bound states, but now we're going to see what it is that the wave functions would have to tell us. And as we go through this, we're going to uncover or discover the origin of a very interesting mystery which had come up in our solution for the energies, and I'll point out exactly what that is in just a moment. But then this mystery that we're going to solve will bring us then to a much deeper and important topic in quantum mechanics, which really begins to get at how we build up fundamental theories of nature and the interactions that describe nature. But before that, let's really focus on this somewhat more mundane but very important topic of how the wave functions behave in our finite square well. So here were the solutions that we had previously. You may recall that previously we were looking at this finite square well, right? It has our classic solution regions, 1, 2, and 3. 1 and 3 are classically forbidden with this curvature constant always curving away from the axis. Region 2 is a classically allowed region that has this curvature constant, which gives me the wave vector describing curvature toward the axis. And K and alpha, of course, are related through our usual right triangle type relationship through this factor Q0, which describes for us then the strength of that height of these potential steps. We then had the form of the mathematical solution for the wave functions, which we had constructed, you will recall, by beginning off in region 1, where we have some kind of an exponential growth, and we really don't have much choice for what we write down in that region, right? We must have exponential growth because otherwise our wave function would be growing or not normalizable as we go off toward infinity. And the only choice we could make at that point then would be the prefactor on that growth, this overall normalization constant, which really doesn't affect the form of the solution, it's just a normalization constant. We had then attached our wave function onto this predetermined growing exponential, matching slope and value, which gives us sine and cosine solutions, but with exactly determined prefactors by matching that boundary condition, and likewise as we then went off into region 3. The point that I'm trying to emphasize right now is that, of course, then there was only one, up to this normalization constant, there's only one possible solution that satisfies this boundary condition off at minus infinity. What we then did is we focused on the behavior of this also predetermined solution in region 3, which is predetermined in terms of hyperbolic cosines and sines with these predetermined prefactors determined by matching our slope and value here. And then what we concerned ourselves with was, well, what conditions are necessary to ensure that I get a normalized wave function? And what we found was that there were only certain energy values, which are equally well characterized by values of k, for which we actually have no exponential growth in region 3, and that then determined for us which were these allowed solutions. What again I'm emphasizing for you here, because it will become useful later in the lecture, I just want to re-emphasize that we do find these special energies where we get exponential decay in both of these classically forbidden regions. But again, there's only one possible solution up to a normalization constant that we find, right? Because we are predetermined by the exponential growth here in region 1. Very good. Now, what was it that we had discovered about the bound state solutions? By looking at the growing and shrinking exponential forms associated with these hyperbolic sines and cosines, we found that the prefactor on the forbidden exponentially growing solution in region 3 could be factorized into a quadratic trigonometric polynomial, which would then factorize in this form. So that prefactor we insisted was 0. We were able to determine it in terms of these various trig functions, and in fact we were able to factor it so that there were two types of solution, a type 1 and a type 2, governed by either one or the other of these trigonometric functions giving me 0. Very good. Now, we then found, by studying a graphical solution to these equations, some very interesting general conclusions. The first of which was that the number of bound states we could read off immediately from our graphical solution, and that it was the least integer function of this ratio of Q0, which measures the potential strength, on pi over 2a. And because it is this least integer function, we are ensured that no matter how weak the potential V naught is, no matter how shallow we make this potential well, there is always going to be at least one solution. There will be at least a ground state bound in this system, and it will be actually of type 1. We further learned that as we go up in energy, if we're fortunate enough to have a deeper potential well where we have multiple solutions, that those solutions show this very interesting pattern where they alternate type 1, type 2, type 1, type 2, and so forth. So there seems to be something very fundamental going on here, right? It's not just by complete accident that we had this very complicated trigonometric polynomial that factored very nicely into these two factors, and that moreover we find that our solutions alternate through the different types. There must be something special going on in the system, and there must be something special about the system then that results in these very special types of solution, type 1 and type 2. And what is going to uncover that for us is when we go ahead and now investigate what the form of our wave functions are going to be. When we incorporate into this general solution, right, which could have exponential growth, we could incorporate there into the fact of the very specific values of k over alpha that allow us to have those very particular allowed bound state solutions. And by looking at what particular values of alpha over k do to our wave functions, we will gain a much better understanding of the nature of those wave functions from the finite square well. So let's then begin that analysis by looking at the behavior of this wave function for those particular bound state energies.